Righty ho, let's do sound test before we get rolling. Sound is good. Just wait for Twitter to catch up and then we'll get started. Boy, we got a fun one tonight.
Modify Rust code bases. Right, there we go. Twitter's just kicked in, so I think we'll just get started. Okay, let's get started because we're gonna have a shorter night tonight. And we're hopefully gonna get 7, 8, and 9 done, and then 10, 11 might definitely gonna be for another day. But we're back to pointers now, so let's see if my brain has forgotten everything to do with pointers. Let's watch this video. So pointers. Okay, so now we know what pointers are, so let's learn it over again. A pointer to pointer in C is just a pointer variable that holds the address of another pointer.
We're now going to get into some more advanced topics for pointers. The first thing that we're going to cover is pointers. Now at first, this seems very complicated. It seems like it's going to be a big hurdle. But when we remember that pointers are just a value that is an address, right? Just like 1234 Sesame Street, that's a value, but we know that it actually is pointing to some other location. A pointer just happens to be an address that points to another address. In the following example, we set up two values, v1 and v2. Just like we've been doing, we're going to set up a name, address, and value for each of them to help us mentally work through what's going on. The first thing is that we have v1. We set that at some address like 4. Okay, it's our beginning address. You wouldn't want to say 0 because that would be null. So it's some address like 4. Obviously, it's going to be a big address later. We'll set that value to 1 so that we can remember v1 for value 1 is that. Do the same thing for v2. Now we're going to get to our first value. That value is checkpoint. And this is what we're going to use along the way to sort of check in to see, after we evaluate certain expressions, what values we get. So first we're going to create a pointer that points to v1. And so, of course, we're going to set that as the value, 0x04, right? Because that's pointing to that address, right? So that's pointer just pointing to v1. Now, if we make a pointer, that is going to be pointing to, or sort of referencing, our original pointer. This is not as tricky as you might think. We're just saying this points to the address of pointer. Okay, so there's no extra magic with this additional layer. We're just pointing back to that original thing. Now we have to ask ourselves, okay, when we double dereference pointer, what is the value going to be? We can use the same tricks that we've been doing before, where we trace through our addresses and eventually get back to 1. When we get 1 here, because we're going to say, aha, we've got a pointer, we go to pointer, we dereference pointer, get back to 1. But what happens when we change pointer to now point to v2? Right, so its new value that's stored in memory is going to be 0x08. Right, we're changing what the value of pointer is. And so now when we trace through, we sort of do our analysis, right? We're starting down here at pointer, and what we're going to do is we're referencing, trace through, and we see now that this points to whatever is in v2, which is going to be 2. So what you can see is that pointers, you should really conceptualize them, at least when we're starting, as just something that points to an address. And all of the same tricks and ideas that we were using before to think about how do we dereference and work with pointers, they're going to do the exact same thing with pointers.
Okay. Makes sense, / not confusing at all, but we'll see. In practice, it might be. This allows you to create complex data structures like arrays of pointers and modify pointers indirectly. The syntax is exactly what you would expect. Pointers to pointers, or pointers to pointers to pointers to pointers, you get the idea, are like a treasure map or a scavenger hunt. You start with one pointer and keep following the chain of addresses until you get to the final value. It's just a chain of dereferences. Okay, so complete the allocate int function. It accepts a pointer. It accepts a pointer to a pointer. It accepts a pointer to a pointer to an integer called pointer and a raw value. Change the value of pointers pointer's address to point to new memory that has the value of the int. So allocate memory for a single integer on the heap and save its address into a new pointer. Oh god, I've already forgotten all the stuff about heap from like last night. Allocate memory for a single pointer on the heap. Oh, I don't remember this. Right, malloc. Yeah, okay, I remember now. Roughly anyway. So allocate memory for a single integer on the heap and save its address to a new pointer. Okay, so int, I guess new, and it's going to be new pointer equals one times size of int. Update the pointer that pointer is pointing at to hold the newly allocated memory address. Update the pointer that pointer. Set the raw value of the integer that pointer now points to. Well, that it points to through 2 address hops to the value passed in. Observe, if you take a look at test does not overwrite in main.c, you'll notice that while pointer does indeed unravel and point to the new value, the original value still exists. It's spot in memory, just don't point to it anymore. So the last one is set the raw value of the integer. Okay, so got a feeling I'm going to be way off with this. Allocate memory for a single integer in the heap. Pretty sure that's it. Update the pointer that pointer is pointing at to hold the newly allocated memory address. Okay. Oh, dang. Surprised I got that. Yeah, so they did the same. Pointer, no pointer if... Alright, I didn't do that part. Whoops. Oh, that wasn't right. I guess I went about it in the wrong way, but still worked. Oh well, I'll take it. Array of pointers. So make an array of integers on the heap is pretty simple. But we could also make an array of pointers. Oh, excuse me. It's quite common to do this in C, especially considering that strings are just pointers to chars. So assignment. Snetclang, being a super robust programming language toolchain, needs to represent tokens, strings of text that represent Snetclang syntax, things like if, else, and def. They're represented as structs. You can see the struct in exercise.h. Take a look at create a token pointer array. Excuse me. It correctly allocates an array of token pointers on the heap, but notice that the addresses it's adding to each index are the addresses of the stack allocated inputs. Update the create token pointer arrays loop to allocate new space for each token on the heap and store the address of the new space in the array. Update the create token pointer array loop to allocate new space for each token on the heap and store the address of the new space in the array. Copy the members from the input struct into the newly allocated one. It correctly allocates an array of token pointers on the heap, but notice that the addresses it's adding to each index are the addresses of the stack allocated inputs. Update to allocate new space for each token on the heap and store the address of the new space in the array. I don't understand this in the slightest. It correctly allocates an array of token pointers on the heap, but notice that the addresses it's adding to each index are the addresses of the stack allocated inputs. The addresses of the stack allocated inputs. Loop to allocate new space for each token on the heap and store the address of the new space in the array. Update. Allocate new space for each token on the heap. Copy the members of the input struct. Into the newly allocated one. Don't understand this in the slightest. Correct allocates an array of token pointers on the heap, but notice that the addresses it's adding here, it's adding to each index are the addresses of the stack allocated inputs. Yeah. Update create token pointer arrays loop to allocate new space for each token on the heap. Okay, new space for each. Copy the members of the input struct into the newly allocated one. I'm gonna have to turn to Boot, so I don't understand this one in the slightest at all. Like, no embarrassment needed, young coder. Let's reason it out together. First, what problem might occur if the array stores pointers to the original tokens that were passed in, especially if those originals live on the stack inside another function? Or you could override them, I guess, or delete them or something, mutate them. Now imagine instead that for each element you allocate a fresh token T on the heap and copy the fields from the input element into that new heap object. Question for you. Inside the loop, how would you allocate space for one token T so that token pointers I points to that new space? After allocating, how would you copy over the literal line and column members from tokens I into the struct? Where in your current loop should those two steps happen? So I'm guessing here. So I guess token underscore T new, I just call it underscore, like new space or something like that, equals how would you copy over oh, I've forgotten. I've added a line. Does that am I going in the right direction? Okay, a couple of guidelines. What types of malloc return? What type should you store in it if you want new space for a token? New space for one token in your line. Why are you using this instead of size token? Oh, I don't know why, to be honest. I just copied that line. After allocating the new space, should token pointers point to tokens or to the fresh allocated space? I suppose it's already a space, isn't it? So once you have allocated token T, how you copy literal, try adjusting the variable type, blah, blah, blah. How are the adjustments? Getting closer, you now allocate press token per slot and storing its pointer. Good. Next question is after allocating new space. What values do its literal, line, and column fields have? How can you set them based on tokens I? Where should you place those assignments relative to the allocation? Also, what should you do if malloc or new space returns null? I suppose, yeah, it's the thing. So if new underscore space equal to null, I don't know, what do we do? Return. How about now? Your function return type is token. What happens if you return inside the loop? What should you return instead, or how else could you handle the allocation failure? After allocating new space, which 3 assignments are still missing, so that the new allocated token mirrors tokens I. Concretely, inside the loop, right after successful allocation, where would you copy literal, line, blah, 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 into new space, and then set token points to accordingly? I guess new underscore space, and what is, whoops, trying to command tab, literal, line, and column. Literal equals, I guess, token, was it tokens I, dot, literal, line, and column. Oh, that's not good at all. Maybe because it has to be pointed to like that. No. Return. I don't know what we return, to be honest. Almost there. Not sure what to do if it fails. When malloc for the array failed, what did you do? Oh, exit 1. Whoops. Exit 1. Is that the answer? Okay, nothing fancy. When in doubt, go for the simple thing that is obvious. See if it works. If it works, then go with it. If it doesn't work, try something else. Void pointers. So we've already discussed void, which essentially means nothing in C. It's used in a few different contexts. Void, update, soldier, blah, 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 means the function returns nothing. Soldier, new soldier, void means the function takes no arguments. And because C likes reusing ideas but with slightly different meanings, the genius of the design can't be understood by us mere mortals. Void also has another use. A void asterisk void pointer tells the compiler that this pointer could point to anything. This is why void pointers are also known as generic pointers. Since void pointers do not have a specific data type, they cannot be directly dereferenced or used in pointer arithmetic without casting them to another pointer type first. Casting to void pointers. Casting to and from void pointers in C is unique because void pointers are type agnostic. When casting a specific type pointer to a void pointer, no type information is retained, allowing the void pointer to point to any data type. However, you must cast a void pointer back to its original type before dereferencing it, as direct dereferencing is not possible. So in number 42, void asterisk a generic pointer equals the address of number. This doesn't work. Generic pointer D value D generic pointer, yeah. This works. It casts to appropriate type before dereferences the value. So HD was the digit, and then it works. A common pattern is to store generic data in one variable. Common pattern is to store generic data in one variable and the type of that data in another variable. This is useful when you need to pass data around without knowing its type at compile time. So type definition enum, data type int or a float, print, void print value. So you pass in a pointer and a data type. If the type is int, we print that. If the type is float, then we put that. Int number 42 equals print value, number in the int, float decimal, and we plus float. Assignment in SNEClang, we have a dynamically interpret SNEC code and we have to dynamically interpret SNEC code and store the values in memory. The SNEC object kind T enum defines the different types of objects that can be stored in memory. Complete the SNEC zero output function. It accepts a generic pointer to one of SNEC int t, SNEC float t, or SNEC bool t. It should zero out the dot value. Value field of the struct by setting it to the zero value of its type. Use the kind parameter to figure out which type of struct you're working with. When working with pointers and dereferencing them, parentheses usage is essential. Consider the following examples. So some struct pointer to field means casting is applied to pointer, and then the field is obtained. Means casting is applied to pointer field. Okay. Into float or bool. Okay. I've forgotten switch statements as well. Yeah, I'm going to give it a try. So I'm going to switch on kind like this, and then I guess case. We'll do integer first. Case, integer. What was it saying? It should zero out the dot value field of the zero out. Zero out. The dot value field of the struct by setting it to the zero value of its type. Use the what? float and a bool. Should zero out the dot value field of the struct. We have to ask Boots this. What do you mean? Zero out. I'm just gonna have to ask that. I have no idea what it means. Like zero out. Greetings, young apprentices. You basically embarked on the quest to understand zero out in the mystical language of Z. When the instruction speaks of zeroing out the dot value, it means to set that field to its zero equivalent. For an int, it's zero. For a float, it's and blah 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 blah. Native approach. But C's bool might need a different approach than just false directly, as the arrow shows. Now let's look at your two. Similar for 0, 0. What does void in the function signature? I guess it doesn't return anything, right? Right. Okay. I think I get it now. So it's going to be what you call it? So it's going to be so it's going to be int to pointer and what was it? Value equals 0, like this. I don't got this. Okay, I see you're grappling with the nuances of void pointers and casting. A common challenge in C. You've made a great step by getting rid of the return statements inside the void function, instead causing those that should not return value errors. Nicely done. Now let's have a look at the new errors. So the expected expression error and the similar ones for float and bool is telling you that the kind isn't a type you can cast to. Kind is an enumeration like integer, blah 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 blah. So int, float, and then boolean. Is none of that right? What? Oops. Boolean. Ugh. Trick explains my friend. It seems the wrestling with the exact syntax for handling void pointers. Let's break down these errors starting with, and a similar. It is not a pointer. Okay, so we don't need that. Don't need that. Don't need that. Is that better? No. When you write, you are casting pointer to an int, a pointer to an integer, then immediately do reference to that pointer, which gives you the value to that pointer. Blah blah blah. Results in an int, not a pointer to a struct. An int doesn't have a dot value member, and that's why the compiler is telling you member reference type is not a pointer. The lesson provides a key hint. Some struct. Getting closer, you adopted the right type point section. However, we stumbled on a new challenge. It's not a structure or a union. This error is telling you that snack object kind is an enum as indicated by blah blah blah, not a struct. Enums don't have members like value. Where? Recall that pointer can point to one of three struct types. Oh, I'm dumb. Right. Okay, I got it. Hey, got me. I'm just getting through on sheer grit and not a lot of understanding right now. Swapping integers. So snacklang makes it easy to wrap to swap two values. So cool person, uncool person, cool person, uncool person, blah blah blah. TJ, cool. Before we do something more tricky, let's start with just swapping some integers. Complete the swap ints function. It accepts two pointers to integers and should swap the values of the integers they point to. You'll need to use a temporary variable to store one of the values while you swap them. So I guess int temp, let's call it a equals a. Yeah. And then it'll be I guess b equals a, and then hold on. Equals b, then b equals a. Is that right? Womp, womp, womp. Two pointers ensures you'll need to use a temporary variable to store one of the values while you swap them. I'm hopeless. Oh no. Swap int. So that's a pointer to into A. So I made a temporary A and then saying A is equal to A is equal to B. I have to do that. No? What am I doing wrong now? Gotta be something so basic, right? Temp temporary A is equal to and then we're saying A equals B and B equals temp A. I'm useless, Boots, help me. I am definitely useless, Boots. You're dragging me along. Looking at code, I can see you understand the concept of using temporary variable to help with the swap, which is great. However, there's a key difference between working with pointer addresses and working with the values that the pointer points to. Right now, you're swapping the pointer addresses themselves, but the function needs to swap the actual integer values that those pointers point to. Think about this. When you have int A, how do you access the actual integer value A is pointing to, what operator do you need to use, and is it the uh, um, pointer pointer conversion assigning. Well, but integers pointer conversion assigning int from int, take the address with the ampersand. No boots, I'm last. Nope, I'm lost. Let me ask you this. When you do A equals B, what exactly are you doing? Are you changing the value A points to, or are you changing where A points to? Think about it this way. If you want to change the value that a pointer points to not change where the pointer points, what operator do you need to use on the left-hand side of the assignment? For example, you want to set the value A points to, is it this? I am so dumb. Why can't I get this? Oh my gosh. Okay, perfect. You're storing the value that A points to. Still changing where A points to, not the value it points to. Great, you're setting the value that B points to. Look at your second line compared to your third line. If in your third line you use blah blah blah, what should you change second line if you wanted to change the value that A points to? What value should assign it to? That. Think about what you're trying to accomplish. You want to put the value that B points to in the location A points to. No. Oh, thank God. get me through this chapter. Holy heck. Oh, just suffering and suffering and suffering. Right, let's take it up a notch. Okay, half a notch, but still. Complete the swap strings function. It swaps the values stored in the string pointers. Remember, char *** is a pointer to a char pointer, which means we can simply switch the address that we're referencing in our swap function. You don't need to use str underscore specific methods for this swap implementation. So what, like A, B equals B, A. Oh my goodness. Is a pointer to a character pointer, which means we can simply switch the address that we're referencing in our swap function. Just like that. Nope. I'm confused again. C code output, what does expression actually do? C does support double style multiple assignment like that? If not, how can you swap the pointers like A, B point to use the step-by-step assignments without losing one of the character values? Would introducing a temporary character help? If so, which value would you go into the temp first, and what should you do with the next two assignments? Writing 3 assignments or just swap? Okay, right, so that whole thing at the beginning was a bloody, like, confusion thing. So, I guess character, temp, it's got A equals A. So then B, then B equals A, like that. Oh my god. The swap strings function, it swaps the values stored in the string pointers. Remember, char is a pointer to a char pointer, which means we can simply switch the address that we're referencing in our swap function. This is getting out of hand. I can see the issue. You're very close, but there's a fundamental misunderstanding about what you're trying to swap. You're trying to swap individual characters using A and B, but the goal is to swap the string pointers themselves. Think about it this way. You have two character pointers that point to different strings. You want to make the first pointer, to the second string and the second pointer to the first string. Key insight, since your function parameters are what do you get when you dereference them once with A, and what type should your temporary variable be to hold one of these values? I guess it's going to be a pointer like that, to that, to that, to that, to that. Okay. Right. Oh God, get me out of here. Generic swap. For the previous swap implementations, we've known the type of the data we want to swap because we knew the type. The compiler knew the sizes of the data we want to swap. However, to make a generic swap, we will need to provide the C compiler with the size of the data that we're swapping, because void asterisk loses that type info. Our new inference for swap will include the size. So void swap and the size. The other problem we're going to have is that directly assigning pointer values does not work in the same way void asterisk. Instead of using pointer equals pointer, we will use memcopy, which is included as so move the data from pointer 2 to pointer 1. We'll use the following. Okay, implement the generic swap function. So allocate memory for a temporary buffer to store the data using malloc. Allocate memory for a temporary buffer. This is going to be void temp buffer equals malloc. That's going to be size times size of size underscore t. If the allocation fails, so if temp underscore buffer is equal to null, then exit 1. Use memcopy to shuffle the data around. Don't forget to free memory after the buffer, so that. And then free temp underscore buffer. Oh. Semicolons everywhere. Whap, whap, whap. Complete fail. So I think I did that. I think I did that to shuffle the data around. Use memcopy. So memcopy. Destination. I guess temp score buffer. We're going to copy and then we'll do temp buffer to VP1. Is that right? Oh. Am I close? Okay, code, I notice a few things. Memory allocation, allocating size, bytes. Whoops. But what do you actually need to allocate? Remember, size already tells you how many bytes you need. Okay. Okay, so we don't need that. The swap logic, you're copying from VP2 to temporary buffer, then from temporary buffer to VP1. But what about the original data in VP1? Where does that go? Oh, we want to swap it, don't we? Whoops. Error handling, it's a bit harsh. The assignment suggests returning early instead. May apply same logic temporary buffer and memcopy. VP1. VP1 gets copied. VP1 is VP2. Then then VP2 becomes temp underscore buffer. Did it? Yay! Oh, thank God. Get me out of there. Jesus. Whoa. So, stack data structures. I think if we can get through this tonight somehow, I'll be a happy man. See what objects look like. Objects is even longer. No. And then what does chapter 9 look like? Oh. This so far has been the hardest course and the hardest module and the I'd say it's probably the least enjoyable one so far. It's very useful, but I'm just like this is total weak spot for me. So I am struggling like crazy to get through this. Right. Right, let's get stuck into this. Let's get stuck into it. Let's try and finish off on a high tonight. Got 6 lessons, let's go. If you've taken our data structures course, you already implemented a stack. We're going to implement a stack again, but this time we're going to do it while manually managing memory of generic pointers. We'll get to have our first deeper exploration of generics in C. Remember that just means void asterisks, as well as creating a data structure we will later use in our mark and sweep garbage collector. Assignment: take a look at snexstack.h, specifically the stack struct. Count is the number of elements in the stack. Size t. Hold on. Count is the number of elements in the stack. Capacity is the number of elements the stack can hold before it needs to be resized in memory. Data is applied to all the generic data. Implement the stack new function. First allocate memory for a new stack struct on the heap. Okay, so I guess new stack equals alloc. If allocation fails, return null. So if new underscore stack is equal to null, then return null. Initialize the count to 0, so new underscore stack underscore stack count equals 0. Initialize capacity to the given value. New stack capacity equals capacity. Initialize the data by allocating enough memory for capacity. Initialize the data by allocating enough memory for capacity, number of void X pointers. If allocation fails, free the stack struct and return null. Return the new stack struct. Return new underscore stack. New underscore stack. Data equals. We're allocating enough memory for capacity number of void X pointers. So if new underscore stack data equals null, then free the stack, free new underscore stack, and return null. Whoops. So that, I'm not sure about that, and that. Let's just see if it works. Hey, I got it. No idea. I was just following the instructions to the letter and not deviating whatsoever. Okay. How are we doing? Oh, I want to be through this so badly. Okay, so let's actually store some data instead of just allocating memory for no practical purpose, aka Haskell programming. So making a room. As you know, our stack has a count and a capacity. What happens when the count is equal to the capacity? We need to make room for more data. We'll take a simple approach. Whenever we run out of capacity, we'll double it. That way we don't have to reallocate memory on every push, for example. Like that. So Simon, complete the stack push function. It safely adds a new object to the top of the stack. Remember, the size of the data array is the capacity of the stack, and the number of elements that are actually in the stack is the count, which is less than or equal to the capacity. If the stack's count is equal to the stack's capacity, so I guess if stack count is equal to stack capacity, then double the stack's capacity, stack capacity equals. Can I just do that? Like stack. Can I do it like that? Star equals 2. Reallocate enough memory for the stack's data using the new capacity. Hit below on how to do this. Double the stack's capacity. Reallocate enough memory for the stack's data using it. The real location function is used to resize memory that was previously allocated with malloc or calloc. It takes a pointer to the old memory and the new size and returns a pointer to the new memory. Okay. Okay, so stack dash data equals relocate or reallocate, I don't know how you put it. Small boy. It's going to be stack data, and then it's going to be if it succeeds, update the DAC state data point field to point to the new memory. Void new memory, and then we say if new underscore memory is equal to null, then I guess exit. Stack data equals new memory. Add the new object to the top of the stack, the counteth element in the array, increment the stack's count. So we do stack data, and then and it's going to be stack count equals object, something like that. How did I get it? Oh no. Oh no. Oh no. What's wrong with my code? It passes the tests. I want to get through this tonight, so I'm not messing around. I'm getting boots in. Okay, I can see your code. The output, the first two tests pass something. It's causing abort which capacity, when capacity needs to grow. When you call reallocate, what point are you passing? Does it point to the array of elements or to the stack struct itself? Point to the array of elements. Are you requesting the new size in bytes for the data array or just the new element count? Okay, files, what happens to capacity when the old data point does the type of new memory match? And count it, so you push the third now, initial question. Yay! See how the solution compares. Whether using pointers. Okay, that. So I just get lucky, basically. Yep, I probably got lucky in that, but it worked. Yikes! Stack pop. So as you should know by now, items go on and off the stack from the same end, last in first out. Don't worry. The pop method is much simpler than the push method in our case because we don't have to worry about resizing the stack. So complete the stack pop function. If the stack is empty, return null. So if stack dash count is equal to 0, then return null. Decrement the stack's count, so stack dash count minus. Return the top element from the stack. So I guess return stack dash data stack dash count. Easy peas. Stack free. In C, we don't have a lot of abstractions in our disposal. There are no classes, destructors, functors, monads, made up category, theory words, etc. We've got data and we've got functions. just the way Dennis Ritchie intended. So to make it easier to work with our stack, we're going to build our own little free function that will clean up all the memory that we've allocated to our stack. So if the stack is null, return immediately. So I guess if stack is equal to null, return immediately. If the stack data is not null, then free the stack data. If the stack data is not null, so if stack dash data is not equal to null, then free the stack data. So free stack dash data, and then free the stack itself. So free stack. Look at how some of this works. I'm sort of understanding. I'm not understanding I'm not getting the use case to use pointers and stuff like that. It's going out of my thing. So dangerous puss. Up until now, even though we made our stack with a void asterisk, you'll notice that we've only stored plain old int pointers. I want to show you how you can actually store anything in the stack, even heterogeneous lists. That being said, this is usually a bad idea. TJ likes to use the words like heterogeneous to keep kids who don't read good at bay. He meant to say you can actually store anything in the stack, even lists of different types of data. Now we're going to do something pretty gross to demonstrate the wise words of one of the philosophers of our time. With great power comes great responsibility. Uncle Ben. He's still dead, okay? Still got shot. Spoiler alert for like 20-30-year-old movie or whatever it is. I'm going to have you push an int, an array of ints, and a regular old int directly onto the stack. A bad idea. I just want to show you that you can store anything in a void asterisk, even values that aren't pointers at all. So complete the scary double push function. So push the value 1337 directly onto the stack using stack push function. You'll need to cast stack push function. You'll need to cast the value to a void. So it's what's the stack push? Stack object. Okay. So stack push, and then it's going to be, what was it? So S, and then it's going to be, what was it? Void asterisk 1337, like that. Allocate memory for a new int on the heap. Oops, forgot semicolon. So I guess int heap equals malloc of int, set the value to which the address points to 1024. Push the int pointer onto the stack using the stack push function. Stack push s heap. Okay, multiple types. So we saw that we can push both int and int star types into the same stack. Again, a bad idea. In this example, we'll see that not only can you push values and pointers into the same stack, but you can also push different types of values into the same stack. This is once again a terrible idea, but the thrust of what we're getting at here is C doesn't care what you put in memory, it spikes all the way down. Fortunately, C doesn't let you do these conversions automatically, but it still lets you do them. When you're working with void asterisk, you're working with raw memory addresses and you can cast them to whatever you want. So complete the stack push multiple types, allocate memory on a heap for a float. So float heap float equals and set the value to which it's pointed to. Okay. Look. And then I guess heap underscore float equals and set the value to which it's pointing to 3.14. Push the flow onto the stack using stack push s and then heap float. Allocate a char on the heap and set the value to which point to snacklang is yeah. How do I do strings again? Strings in C. I'm not sure about heap assignment to strings. It's the only bit I'm not sure about this part. Okay, so a few guided questions. What does it declare? An array of 28 pointers or a single pointer to char? If you want a single heaped allocate string, you should just allocate space for one character or all characters plus a null terminator after allocating blah, blah, blah. Assigning characters into your buffer, or is it to try and an array of 28 pointers or a single pointer to a character? If you want a single heaped C string, you should allocate space for just one character or for all characters plus the null terminator. I'm not sure. A single character or it's a point. So in C, it's a pointer to the first character in the string literal. If heap character is a char, what does heap char refer to versus heap char itself? After allocating enough bytes for the whole string, crap. Compute the needed size with yeah. Allocate that many bytes. Use a string copy function to copy it to heap char. Oh. Whoops. What's the string copy function? I don't remember what it is. I'm asking you, Boots. String copy. String copy. Copies a source string to a destination string. So each char. Ugh, mind melter. Boom, and just like that, we're on to snack objects. We got 9 lessons in that, so we're not getting into this now. We've got 3 lessons left. That's going to be one. It's going to be one session next week to basically smash us out because my brain is fried. Yeah, we started off later today. Made good progress, but to be honest, it's just time to end it now. We're at time, but we're getting closer. So thanks for coming down. Hope you had fun watching me suffer through advanced pointers and everything from C. It's like very, very fresh. I'm still getting used to it. I'm probably never going to use it again, to be honest, but it's nice to go through it once and at least be sort of like understand when I'm reading the code, even if I can't write it very well. So tune in next week. There's no more sessions this week, no more streaming nights. So tune in next week where we're going to wrap this up, hopefully in one night, make it a long one. And then we're moving on to a new module in the course and smashing through that. So thanks for coming. Have a good night and see you next time. Auf Wiedersehen.